Another draft physics video presentation. I figured I'd do comments just separate, as they're mostly trolly, and there's no point in soiling other videos with the comment videos, so I probably should keep them separate. So I will. As somebody requests, essentially. So Donnie Sundley says, have you watched the latest Physics Girl video where she just visited CERN? Yeah, and the one before that was like two before that or whatever. She visited LIGO 4 years or whatever, after the fact. And the analysis was, oh, this is so exciting. I mean, it's not really a useful, you know. The explanations are simplistic, and none of the real questions are answered in terms of how the thing works or how do you know you're right, that kind of stuff. So I'm sure there was no question in the video she did from CERN about something like, how do you know it was a Higgs boson? Are you sure? How sure can you be, really? The whole theory is crap. So anyway, particle accelerators really haven't been interesting forever. Yeah, I never, so it all depends on what you think they're seeing. So you think when they have a car wreck, they smash particles into particles, that they're seeing a bunch of real stuff fly off and blah, 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 blah. And I'm sort of arguing, no, there's no antiparticles and no positrons, and, well, they never saw any of those. And of course, they never saw any quarks even, and they never even saw a Higgs boson. They never saw any of this stuff. They just conjecture, based on the other pieces flying off in certain ways with certain velocities, that something must have made that happen. And they make up a story for how it happened. So you think it's great physics? Fine. I don't think it gets anywhere. I don't think it certainly helps in understanding elementally how electrons and protons create atoms and how atoms interact. I think you're much better dissecting what chemistry does, like coming up with a model that explains why lithium is lithium and helium is helium, and why the different elements, steel is steel and nickel, and all that kind of stuff. Explain why those things are what they are based on their chemistry. That would be a lot more interesting, I think, which they have done to some extent, in terms of understanding how carbon arranges itself to create what we call diamond, so that the element isn't really, it's a little tricky when you say what's carbon, because you got graphite and you got diamond, and it's both the same stuff, pure. It's just in a different arrangement, and it makes a huge difference how it associates. And that's in a lot of chemistry in kind of hidden ways, in the sense that, until a few years ago, I didn't know that hydrogen really doesn't exist as individual hydrogen atoms. It exists as two hydrogen atoms stuck together more commonly. So anyway, those are just little bits of stuff. But yes, if you think CERN is terribly interesting, fine. I don't think any of it has any real value. I think it's all just a place where you go to look into a little funny glass window or something, and and it's like a crystal ball and has all kinds of stuff flying around in it, but you can't make anything out of it. It's just full of ghosts. And so yeah, you can make up any story you want after you walk away. So whatever. That's the fact that I understand what accelerators do. They sort of changed over the years. Originally they were just linear straight lines, and you would just keep trying to you keep putting the particles through a voltage gap to keep increasing their voltage. And they learned they can spin them around by putting magnets around, and in doing so, they can make the circle smaller and smaller and smaller, and increase the velocity by making the circle they're spinning in smaller and smaller and smaller. Then they figured out they could put one set of particles going one way in the circle and another set going the opposite way, and that they could make them crash into each other and then double their energy of their collisions. But again, what are they colliding and what are they getting out of the collision is the question. They don't really understand the distinction between matter and force, stuff that moves the speed of light and stuff that doesn't. And so they have a whole bunch of particles they think they find, and I would argue that they're playing a game like hydrogen. A muon isn't just an electron. Okay, it's an electron with a bunch of stuff trailing behind it. It's a collection of energy that has an electron in the front. It's a bunch of little force pushing that electron. But anyway, whatever. People can believe whatever little bullshit you want to believe. So then Jackie the Joke Man Marlowe. So like it's a joke of some kind about a joke, about something that isn't even funny, right? Like Jackie the Joke Man is like famously unfunny. He's like the most unfunny comic ever. His name is Martling, I think. So I don't know what this Marlowe is. I mean, what is this? This is how you occupy your day, is creating these bizarrely stupid fake sock accounts, and then so you can make these inanely weak and empty crap comments, and that's what you call winning. Yeah. Somebody must have pointed out to you before that you're psychotic or retarded, right? Like everybody you've met. Anyway, of course, he has watched it. It's a YouTube video about physics. Well, I wish it was about physics. It's really not about anything real. It's a little fairy physics. Again, they call it particle physics. It's not even about particles. It's about giving things that aren't particles a name like they were a particle, because all they think is everything has a frequency, some wavicle. How does that mean he understands how CERN works? No, does that? Now, does that mean? So again, understanding how it works, what, like the billions of dollars they pumped into it, but that's like Lego. You people don't care how it works either. You don't care about what assumptions are built in. You don't want to do any scrutiny at all. You just want to say, oh yeah, they're always right. They're always right. Right? That's all you're saying, is they're always right. The Pope is always right. And you think that should impress somebody. Yeah, so, sorry. So we'll remove for now. And I'll remove this question. I mean, like I said, this video really isn't devoted to high energy physics nonsense. It's arguing their elemental understanding. They haven't got the distinction between force and matter right. They don't even understand that the magnetic monopoles are just as real as the electric monopoles, and they exist in the atom, and they're called electrons and protons. They haven't even got that story right. All right. Kyle. Damn, I was excited to see what you had to say about what a photon is. Yeah, it's video number 17. Yes, yeah. And there's other videos that are more about what a photon is. The purpose of these particular videos is point out the distinction between their theory and my theory, and to demonstrate just how bizarre their theory is of some giant wavy thing that interacts with single electrons in some magical way that can't be rationally explained. Okay. Let's see what you had to say about what a photon is. But 10 minutes in, and all you have done is talk about how stupid other people are. Well, that's not really what I did. I was reading comments like yours, asshole. I mean, I said right in the video, I'm going to read comments now. And you're whining and complaining. Jump ahead if you don't want to listen to comments. It's pretty obvious how the routine goes. So you obviously haven't watched. You see the 17, and you see number 17 in the title, and you don't realize it's a series of videos, and that all you have to do is jump ahead in the video if you want to get to the part where I'm playing his video and critiquing it. But again, and isn't it your obligation to point out when somebody's saying something wrong? So nobody should tell anybody else you're wrong. Everybody should just accept whatever they say. Yeah, okay. Fuck you. You sure aren't one of them yourself. Yeah, that's my whole argument. I'm presenting evidence. Now, do you have evidence? Can you actually articulate a reason why I'm wrong about something, or I've said something wrong, or said something stupid? Could you actually articulate it and explain? I mean, go to the trouble that I'm going to explain why they're stupid. I'm not just saying they're stupid like you, stupid. Stupid is just saying you're stupid. Or stupid is just saying we're right. Now, the Van Briesen guy doesn't really get into theory much. He's just teaching the Bible. He's just reading the Bible and then writing it on the board kind of thing. So he doesn't think about it too much. A little bit. You can see a little bit where he has some trouble with it. He's saying, well, this whole particle wave thing doesn't work because whatever this fucking thing is, it's I can't understand it as either. So that's his problem. And the reason why they can't understand is the particles because they've invented some dopey notion that something has to interfere with something else, when that doesn't have to be the explanation. But anyway, there's no value to your comment. It's useless. I could type it on anybody's video. Just nonsense, whiny crap. So what am I to say? Fuck you. Alright, he's batshit insane. Again, proven with nothing. They can't come up with a single... They can't show or quote something. They say, you can't say what I've said that's batshit insane about physics. Where they can say anything. They can say many worlds. They can say photons have radar. They can say, yes, photons destructively interfere when it doesn't make any sense. They can't destroy each other. They can say electrons and positrons annihilate. Well, not really, because they can pop out of nothing. They can just poof right out of space. Just all of a sudden, they're just, whoop, there they are, poofed right out of space. That's their theory. That's the stuff they're saying. And you don't think anybody should counter-argue it and say, nah, wait a minute. I mean, you're pathetic examples of human. You just point out how, yes, humans are just shit-talking asswipes. I mean, here they are ridiculing somebody for making an argument, standing up and saying, look, this is my argument, this is my evidence. Show me how I'm wrong. And you show me how I'm wrong by just calling me names. Nothing else. You provide nothing. No reasoning whatsoever. No demonstration of how I'm looking at it wrong. No, you're seeing it all wrong. This is the right explanation, see? You don't have anything. You have zero. I ask you to show me how the interferometer works. Show me a picture of how a photon goes through. Show me what a photon is, why don't you? Why don't you explain how it doesn't matter how long the ray is? We don't care. But that's your physics you're defending. Show me some bent space doing its thing. Show me how the bent space moves the object. How every electron and proton inside realizes, oh, I'm in bent space and I have to go that way. Why don't you draw me a picture of how that works? That doesn't look like magic. God, people are just such pieces of suck. Ugh. So. Ugh. Alright. Near-term extinction. I thought I already did him. In my opinion, yes, okay, I did do him. Yeah, it just got pushed down again. Alright. You said current carrying does make sense. Okay, so, yeah, this one's right. Alright, at 29, so he's time coding again. Oh, he's a very good typer, though. All this typing. You misread a sentence in my comment. So what? Probably isn't that important. I said your explanation for the current carrying wire does make sense. Not that it doesn't make sense. Well, again, you're just putting... The whole tone of your comment wasn't very clear. And it was still just proposing as if there's still, all this uncertainty, we can't figure it out. I've given you a rational definition of how magnets work. It works. And they don't have anything close. I mean, not even close. I've given you a theory of gravity that fixes problems like drag and gets rid of any other question, in the sense of I'm pointing out how you can see the storage of the energy. You can see how the Earth is absorbing energy, because guess what? It's hot inside. And the heat is evidence of energy that's been absorbed. The energy had to come from somewhere. It always has to come from somewhere. Right? Something doesn't push into something else. Something doesn't become a little ball unless it's absorbing energy from somewhere else. All right, anyway. Having said that, I'm not claiming I fully understand your explanation. Okay, well, whether you fully understand or don't fully understand, I guess I can't fill in the blanks unless you're more specific about what the blanks are, what the parts are that are confusing you. Because, frankly, I don't understand how there's any confusion. Once you've accepted a couple of my axioms, it all falls into place. I mean, it's 2 plus 2 plus 2 physics. The fact is that all you need is 2 kinds of force and then 2 kinds of charge, plus and minus, and 2 objects that behave inversely to the plus and minus. That is, the blue force hits, they attract, the red force hits, they repel kind of argument. It's not exactly how it happens, but I'm just saying they're 2 inverse reactions. And once you have that, you have the explanation of the entire electromagnetic phenomenon. And you're done. I mean, all you need is the 2 interactions, the 2 electron and proton, and 2 forces, 2 bits, 2 kinds of force that provide you an inverse reaction, an opposite reaction, or however you want to say it, a fundamentally different reaction. Well, different. Doesn't even have to be fundamentally different. And it explains this whole process of I mean, even you could concede, I just would think even without a replacement theory, you could sort of understand that they don't really emphasize charge as the origin of everything, but charge is the origin. That's where it all comes from, is the existence of the complete difference between an electron and a proton. And you know they're different even by conventional theory, that they're kind of opposite each other. Anyway. I'm not claiming to, I mean, simple things. I mean, I can tell you that push has no, it doesn't violate any rule to be a fundamental mechanism. Okay? It doesn't need any extra mechanism. You can understand push. One thing banging into another doesn't violate doesn't screw up in terms of being definable as a fundamental event. Where pull, okay, you just can't describe a pull without implying some other infrastructure, a lot of infrastructure, some sort of magic or some sort of mechanical infrastructure that makes it possible for something to grasp something and then pull it and do all that kind of stuff. So, I mean, there's no, those are simple arguments. And you should be able to say, yeah, physics really hasn't accounted for any of that. The fact that all the forces move the same speed. I mean, how can you have bent space and virtual photons and they move at exactly the same speed? I mean, what sense does that make? 2 fundamentally different mechanisms functioning exactly at the same speed? I mean, come on. I mean, most of these critiques of their theory don't even need a counter theory. And the point I'm making to you is that there is a reasonable counter theory. This is just as bad as religion, right? Religion is a stupid story on its face. Even if if you have no geological evidence, you have no evidence for evolution, it's still a silly story. And lots of human beings in the history of mankind realized that before Darwin. Darwin's grandfather believed in evolution, right? He didn't need a ton of evidence because he knew the God story was silly. Anyway, but that's due to my ignorance of the details of how current works and how it affects. Well, like I said, I still have some incomplete. I can't give you complete answers because guess what? It is kind of complicated. But eventually, the simulations are being worked on, and they may provide a mechanism for getting to more exact function, just because as the simulation develops, any flaw is going to be made obvious. So anything you get wrong is going to show itself, and that's very helpful. But being that there really is no evidence experiment that directly tests the motion that tests the notion that moving charges produce magnetic fields. Yes, and so that should be really big to you in the sense that they're asserting a truth like they know it to be the facts when they don't have any experimental evidence. They don't have anything that makes it make any sense. again, they're not, they never talk about a magnet filtering a force. They talk about a magnet making a virtual photons. There's this magical thing that takes place. You know, when it seems kind of obvious that what magnets are doing is filtering. All right, anyway. Their conventional explanation for the current carrying wire is unwarranted. Their confidence in their explanation is unwarranted, and their explanation is incomplete at best and incomprehensible, I would argue, by common sense standards. Although, to be fair, I'm not sure what the current of an electron beam is. Exactly. I don't think they are either. But anyway, it doesn't matter. The fact is, it's moving charge because you can bend it. So it's obviously got to be charged, and clearly it does move. So it's definitely moving charge, but clearly it's not creating another magnetic field. So you need the atoms for that. But I think it is very low, on the order of milliamps. I don't know what, so I don't think that's true at all. I mean, I think it takes quite a bit of voltage, actually, and in turn amperage, you know, to produce a very substantial electron beam. So I think it has watts worth of power. So maybe it's possible that the electron, I mean, that's why the old tube televisions, you know, they did waste a lot. I mean, there's a lot of heat. But yeah, obviously it did have to pump quite a bit of voltage in to get tubes to work. So maybe it's possible that the electron beam does produce a magnetic field, but since the current is low, the magnetic field is not easily detectable. Well, again, it's sort of always comes down to watts, right? But the argument is that yes, I mean, it's obviously going to be higher voltage to get a good gap to shoot electrons across. You need a lot of voltage to shoot them across any kind of, you know, substantial distance. But I think, you know, it depends on the instrument you're using, so, and how far you need them to go. But yes, obviously the higher the voltage, then yes, the less bits themselves will be moving, but they are the pure charges, so in a sense they don't have the liability of having all the atoms from the conductor to dilute their magnetic field, so they should in a sense make it even more purely. It should be an even more pure effect because there's less atoms in the way. All right, but anyway, who wants, you know, this is arguing minutia. But since the current is low, the magnetic field is not easily detectable, but it certainly makes sense to think that the current is having an effect on the material of the wire in order to make the wire magnetic. Yes, and the effect is doing what? It's polarizing the atoms. For the atoms to transfer pressure, they have to be pressurized in some uneven manner. That is, an atom here has got so much pressure, and the one right next to it has less pressure, and the pressure is going to be conveyed from one atom to the next, and cascade, just like electricity cascades through the material. Okay, again, I'm also not claiming to fully understand this effect that current has on the wire. So again, it has an effect on the atoms. It's always got to go back to the atoms. In your view, all right, you don't fully understand my view. Well, my view is pretty simple, but let me just say it for clarity. I mean, sometimes I'm playing with this idea of something blocking something and then something being closer to something, and so I think to nail that down a little tighter, the argument would be, let's see, oh, that's very yellow. Yeah, I should be able to see that. Let me use blue. That's the contrasting color. All right, so the idea would be, is what we're talking about is pressure and how it's created. And so in paramagnetism, you could argue that this is the electron and this is the proton. And you could argue that the surface of the material is going to have, these electrons are going to be making up the surface. the outside of atoms, they're going to be more regularly on the surface. And the idea of paramagnetism is you're going to move these in opposite directions. So that's, you put a north side here, you're going to push this electron in, right? And you're going to pull the proton this way a little bit. All right, so you're going to do inverse actions. So if I put a south pole, do that, the electron is going to be pushed. The electron is going to be pushed out this way, so they're going to get further apart from each other rather than closer to each other. But for the sake of argument, let's just do the north again. So you understand, it'd be the opposite effect. So the point would be is that if you could see this thing as radiating energy, and then if you recognize that this thing is going to essentially change this energy into energy going this way, into energy, say, going this way, right? So everything that hits this ends up going somewhere else. So it's not going to go out here anymore, right? So you have a certain amount of energy that gets out here. And then this thing's also making energy. That is, it's reflecting energy to the world. And so the idea is as I bring this closer to this, I'm blocking more of the source, right? The source is here. So as I bring this closer to the center of gravity, I'm bringing it closer to the source, which means I'm wiping out more and more of these angles. So I'm removing yellow from getting out, and by contrast, the blue I'm emitting is now going to be stronger because now there's less yellow in it, if you get me drift. So if these things were blue and yellow, right, you could imagine that depending on how, so just depending on how close I put the electron, right, if I have it very close, I'm going to block a lot of the yellow, and what am I going to get coming out? I'm going to get something that looks more blue than yellow. And if I have the electron very far away, then I'm going to end up with a field that's going to look more yellow, okay, than blue. So that's sort of the argument. So it's how green it's going to look. It's going to look blue-green from here, and it's going to look yellow-green from up here, right? So that would be the difference as you move just the electron closer and further away from a proton. That would be the net effect, is to dilute one force, okay, essentially. So the closer I bring the electron, the point would be is more of this yellow is going to go this way or this way. And the further away the electron is, the less of the yellow is going this way and this way. That's the theory. Yeah, because you won't be changing how much of the blue, because you can only change how much of the yellow from this diagram. And so that's what makes charge interesting, is it can have these subtle changes, and then it can have more dramatic ones where you can make this all blue versus being green, you know, a shade of green. But anyway, that's the principle. So the principle in paramagnetism is essentially what happens in paramagnetism is that you put some negative force, like an electron, near these electrons. They repel. That pushes this electron closer to the proton, which makes the atom more electron strong than proton energy. So in a sense, it's becoming, even though the electron is further away, okay, by going further away, it's diluting the opposite force that's creating any kind of attraction. So it's eliminating the attractive force, and all you have left is the reflective force between the two electrons. So now you have a force away, you have the normal magnetic effect. So even though you moved it further away, the byproduct of moving it further away when you're moving it closer to a proton is that you're weakening the pull force, in this essence the force that would eliminate energy between the two, and strengthening the You don't even have to strengthen it because this is a direct relationship. Protons and electrons don't interact with each other by the inverse square law. They're not like a big solid charged object. They interact by simply, it doesn't matter how far away they get in some respects, because the only thing their distance changes is how fast something bounces back and forth between them. It doesn't eliminate it or add to it, except in the sense that it adds the number of impacts and the amount of pressure. But it doesn't make the force go away. Another way of saying that, I suppose. Well, anyway, so this is the simple, but I like, all of this gets kind of complicated, because you say, well, what about this and what about that? The side effects that are created by this going sideways even. And then you can have a whole story about the other atoms have to be, the atoms have to be arranged with each other out of sequence. That is if you have protons and electrons in these kind of arrangements, well, that means they're always staggered, and the protons are going to be on one line and the electrons on another, and a proton and an electron, and that ends up being a kind of polarization, because then any of this excess energy ends up taking a right turn and then going this way, and then takes this turn and goes that way, and you can go through a whole explanations of all the consequences. But anyway, that's the brief of it. Yes, in concept. So anyway, so the point is that in a magnetic field, the real trick is, right, you can move the magnet, and then once the magnet stops moving, all the electricity stops. Any polarization of the atoms stop. And that's because the atoms just find this condition, and now all the atoms can't pass it on because all the atoms are in the same condition. So they can't pass on pressure if they're all at the same pressure. Alright, although the material of the wire making okay, again, I'm also not claiming to fully understand the effect that current has on a wire in your view. But that is due to my lack of detailed knowledge as well as lack of direct experience with tinkering with circuits. Okay. Whoa, look at all this stuff. Whoa. Okay, anyway, I have another question. Okay. At 31, you said that if you bring the north pole of a magnet up to an electron, then every single time the electron is going to jump away from it. But this isn't the case. But isn't it the case that magnets have no effect on stationary charges? No, that's not the case. I'm saying you can create charge on an object, and you can bring a magnet in proximity to the charge, and you'll move the charged object. It's just that the depth of the magnetic field isn't the same as a charge field. A charge doesn't have any dilution in it. A magnet's always carrying a diluted field. It's one of the reasons. But negative and north sides of magnets will always repel negative charges. Okay, once again, the motion of the magnetic field. Once again, the notion that the magnetic field have no effect on stationary charges is from conventional physics. Well, it's just plain wrong. So I don't know where you got it from. Like I said, if you charge something, you can manipulate it with a magnet, and it will manipulate a magnet. That's why the compass needles will move in an electric field. So I don't see where they have evidence of that. Yeah, I don't see. I mean, the whole point is you're manipulating like electrons by creating a magnetic field to move them. So how can they not move? The only way you can manipulate electrons is to manipulate them with a magnetic field. Yeah, you have to manipulate the charge, and the magnetic field does that, whether they're moving or not moving. They make them moving because you need them to move to have changes in pressure. You have to change the pressure. You have to move something. So, I mean, you can just do it with a magnet. If I want the current to go one way, I just push the north side of the magnet this way. I'll make the current go the same way I'm pushing. If I push the opposite way, I'll have the current go the opposite way. I mean, clearly the magnet's just pushing the electrons. All right. Right, so once again, the notion that the magnetic field has no effect on stationary charges from conventional physics. Right, but I don't know of any experiment that demonstrates that. But this notion seems very testable. I'm just saying, there's no experiment I've ever seen where something charged isn't affected by a magnet. All right, can't they just bring a magnet toward a charged conductor surface and see what happens to the charge distribution by checking the voltage? Well, the point is obviously charge is a measure of voltage, right? Voltage is telling you how charged it is, that is, how north it is or how south it is in magnetic terms. So obviously something weakly charged is not going to be, you're not going to get very far trying to move it around with a magnet. How else to say that? And magnets are, it's hard to make. Magnets, charge is on a surface, so it has a huge density in terms of its profile if you put charge on a physical object. Magnetism is the atoms themselves, and it's hard to make a big giant magnet. But if you make a big giant magnet and then charge some balloons or something, you'll see the balloons, fly in different directions depending on where they are in configuration to the magnet. Yeah. It's hard to make them proportionally, spatially consistent, because the magnet has got a lot less. It has a lot more dead electrons and protons in it than the surface of something that's charged. Its mirrors is really kind of a much purer mirror, in the sense that it's all charged. Wherever you look on the surface is kind of a mirror, where the magnet is creating a mirror on a smaller surface, but it's creating it from an internal mechanism. Let's see how to explain that. Yeah, it's just a lot. It's a lot harder. The filter has to work a lot harder, the dipole filter, than the monopole filter, if you can make a monopole filter. Yeah, charge just goes further. The effect of a charge moves further because it's not diluted. All right. They can't just bring a magnet towards a charged conductor surface. Can't they just bring a magnet toward a charged conductor surface? Well, a conductor doesn't charge very well, but okay. And see, I mean, obviously you have to keep it insulated to charge it, where a non-conductor holds charge on surfaces better. And see what happens to the charge distribution by checking the voltage. I don't know exactly what that means, but okay. Is there any evidence that a magnet is affecting a stationary charge? One of them has to move, right, for them to be moved into proximity to each other. So it's kind of hard, I mean, there's lots of evidence. You move the magnet or you move the wire. It doesn't matter which one you're moving. You're going to create electricity in the wire. But let's see, how do I make any? But the point is that you also have to have some place for the charge to go. And you have to keep pushing. So the movement, the field, everything just moves adjust to the new field. So if you're going to allow the current to go through the wire, then the readjustment will be made. And until you allow everything to bounce back, that is, all the atoms to go back to where they want to be or arranged how they want to be, they can't be pushed again. I mean, once you've distorted them, you have to let them undistort before you can distort them again. That's why alternating current works. Anyway. Of course, if we throw out the conventional notion of moving charges producing magnetic fields, well, the argument is the charge, electrons and protons, produce a field no matter where they are or what speed they're moving. It just doesn't matter. They're always what they are as a charge. They're opposite mirrors. One reflects blue, one reflects red. If you think about it in those terms, there are always those things, and yes, there's a consequence to moving the mirror. Magnetic fields are no longer distinguish between moving and stationary charges. Then there is evidence of moving charges. Specifically, electron beams being deflected in a magnetic field, although not a vacuum. Being deflected in a magnetic field, although not in a vacuum. For example, check out this video of a cathode ray being deflected by a bar magnet. Right, I don't need to check it out. We already know that's a consequence of, even if they were not moving, those charges would move. So even if I could take those electrons and they weren't moving, streaming past, but I could just put a bunch of electrons in front of, looking like a beam, they'd all disperse as soon as I put the magnet near them. They don't need to be moving to be moved by the magnet, the force the magnet's irradiating. The red force hits the red mirrors, and the mirrors reflect the energy, which means they absorb momentum in the opposite direction. So anyway, you see that the beam bends one way when the north end is pointing towards it, and bends the opposite way when the south pole pointed towards it. Right, but more importantly is how those experiments are done, right? So if they do it in a vacuum, the beam moves away or towards. If they do it in a vacuum with atoms in it, then you see atoms that'll move up and down, because now we're back to a conductor again. All right, we're back to the fact that the motor force is the complication, where instead of moving towards, when they're in a field where atoms are dipoles, so that means one side's doing one thing, the other side's doing the opposite thing, and you put in an opposite field, what's going to be the result? So the one to find, you want to find an experiment, or you can answer one of my questions for a change. The interesting question, the one I don't know an answer to. Gee, it's just not erasing very effectively. But who cares? Alright, it'll be good enough. Anyway, alright, so the idea is you have a north and south magnet, okay, a magnetic field, and you put a wire in here and you run current into the board or whatever, it doesn't matter. If I run it into the board, the wire goes up. If I run the current out of the wire towards you, then the wire goes down. Let's say that's the rule. I might have it backwards, but it doesn't matter. The thing I'd be curious about is if you take this and just change it to two stick magnets, So you just put the north end here and then the north end of this magnet over here. So what's it do? What's the wire do when it's in two north magnets? See, because I'm saying this has to do with paramagnetism. That the first effect is to paramagnetize the wire, and by doing that, these atoms become already polarized, and now the current is feeling the polarization, changing the field, and that's what's creating the energy to move in one direction or the other. But I would be curious, if it's two south ends, does the wire move down? If it's two north ends, does the wire move up? So if somebody has that answer, it's a pretty simple experiment. You think somebody would have done it. I just haven't found it. Alright. I mean, I guess I should be able to do it. I mean, I just have to get some decent sized magnets and run enough current through them. A wire. Alright, here we go. You see that the beam bends one way or north and pointing, right, and bends, right. But that's not, again, see, this is where, these subtleties matter. I mean, when you put a gas into the evacuated electron gun beam thing, you are changing what you're seeing. Because now you're seeing the electrons because they're exciting atoms and then creating photons. So the only part of the beam you're seeing is the part that's hitting an atom. So you're seeing what atoms do in the field. You're not seeing what electrons do, but you can't see the electrons. Now, if you use a completely evacuated tube and then use a piece of fluorescent material to have the electrons hit, and then you can see where the electrons are because they hit the material that fluoresces. But see, you just can't see the electrons on their own. You only see the electrons if you make them hit something. And that's the flaw in the experiment, is the only photons you can see are the ones that hit something. And there's no like kind of simple dust you can put into the evacuated tube, that's fine enough, smaller than the electrons, to make it possible for you to see the electrons without them having to hit something bigger than they are. That's sort of the problem. All right. Points towards it. But the force experienced by the cathode ray is known as the Lorentz force, which explains how the force is in the transverse direction, right-hand rule. Well, it's not really transverse, but it's the plane of the interaction is these two dimensions, and the force is moving the object in the third dimension. That's the funky part. It's not moving towards or away from the field it's in. It's moving transverse to the field it's in, and that's the part that's weird. All right, but it's only just another dimension. You can almost argue too, though. I mean, if the rule is, you're hitting a brick wall, you have a choice, right? You go up the wall, you go down the wall, you go left, or you go right. It's that kind of obvious thing. So, just as there's no common sense rule that says, oh yeah, right is preferable to going up. But obviously in the physics, there's a reason why it doesn't go right or left and instead goes up and down. And that's why there's a right-hand rule. It exists because there's obviously a prejudice for that one event to always take place, for it to always turn right instead of going left or up. Anyway, similarity between a current carrying wire and a cathode ray is that they both experience this Lorentz force, but only in the circumstance, again, where there's atoms in to see the ray. And that's, I would argue, is the huge liability in the experiment, is the existence of those atoms. Because now you're seeing where atoms are going. You're not seeing where the electrons went. Now, since the cathode ray in this video is going through argon gas, there you go. Good that you're picking it up, which is the reason we can see it in the first place, as what we are seeing is ionized argon. Right. It still seems to be consistent with your view, although correct me if I'm wrong. Well, I guess, yes, I'm clearly consistent with my view that atoms are going to be different than the constituents of atoms. So, yes. Since the electron beam in the cathode ray tube is ionizing the argon atoms in its path, and the question would be, is it creating negative ions or positive ions? And that would be part of the conversation. Is it the case that it's also polarizing the atoms, and therefore, well, you can't be an ion without kind of by definition being lopsided, polarized. Therefore, the magnet is really bending the polarized argon atoms and not the electrons themselves. Yeah, that would be a potentially viable explanation, yes. If not, then why would the cathode ray be experiencing the same Lorentz force that the current carrying wire experiences? I would argue that if there's a reason that I'd say monopoles would be hard to explain. Okay, so this classic motor force experiment, where the wire goes up or the wire goes down. Now, if I put an electron in a field that this is the south and this is the north, if the electron went down, that wouldn't make any sense, right? I mean, it'd be pretty hard to figure out why did the electron go down or why does the proton go up if the force is clearly positive here and negative here, it's going to go to the positive side, and then vice versa to the negative, the north side. So it wouldn't make much sense. So obviously it has to do with when you put current through. When current's moving through a wire, it's clearly doing it in some way that has a turn to it, or it has an imbalance that's always canted. Like it always starts at the 12 o'clock, but it always starts counting this way, always with a bias. And so there's always more negative, more back sides of the magnet show on one side and more front sides to the magnet show on the other side. There's no way to get a 50-50, but you can't cut the magnets in half. So there's always a bias with a whole magnet on one side going this way and a bias down on the bottom with a whole magnet going this way. So it has one extra magnet on each side, but you can't cut the magnets in half. It's like if they were atoms, you'd be stuck with that as a dilemma, right? I mean, if you tried to make a circle out of the atoms, and the argument is you can't start with anything but a whole atom, then your one position, your position off 0 would have to be a whole atom is where you started. So you can't have like an even number at the end. Might be why there's no answer to pi, is because it's impossible to create a start, okay, without having a broken, a non-existent middle, because you'd be halfway through an atom, and you can't be halfway through an atom. All right, but don't electron beams get deflected like this even in a vacuum without any gas? Well, no, they don't. They deflect in and out, they deflect north-south, like repulsed or attracted. That's my understanding. That's what I've seen. So if you want to just see them, if you just, without a gas, if you put a magnet towards the beam, it bends the beam away. The north side bends them away, the plus side bends them towards. Okay, and if that's the case, then why should the electron beam deflect according to the same Lorentz force experienced by the current carrying wire? Well, it is proving what's the case, I guess, is the obligation somewhere. They certainly don't prove it. So yeah, I have to go out and go find all the video evidence I can, I guess, to demonstrate which is the truth. So yes, you have to go out and find the experiments, and I'm just going by what I've seen, is that if they use the fluorescent material, the phosphorus, and shoot the beam, so part of the beam hits the phosphorus to light it up so you can see where the beam is, and then they put a magnet in, they can move the beam up and down by just putting a magnet, and it'll move traditional. If they use a gas to see the beam, then you can do let's put 2 magnets in this way and make the beam go up, and let's put 2 magnets in that way and make the beam go down. Just switch the magnets. All right. So Jackie, the joke man, with the wrong name again. Let's see. Would you consider what you're doing to be more physics or philosophy of physics? So clearly I'm doing physics in the sense I'm arguing the fundamental experiments that are described as physics. So whoa, how are you confused? Oh, that's right, you're not. You're just being rude. Because I never see you doing physics on the channel. So again, what did I just do? It wasn't physics? What was it then? Asshole. I mean, idiot. I mean, crazy fuck. I mean, I go to the trouble. I showed you the experiment on the mesons, and I pointed out just a couple of questions the video raises. Did any of you choose to answer my questions? No. I mean, I'm asking them, what do you think of that? I mean, how do you think they can estimate exactly how many bricks the atmosphere is made out of? You didn't answer. Okay, I see you talking about how stupid people are, or about your own personal philosophy of physics. Well, I don't care what you see is really quite irrelevant, because obviously you can't see straight. You need brain glasses. You need them really bad. All right, we'll remove that for now. All right, as an anecdote, John von Neumann, who was integral in the development of linear algebra conception of QM. And again, that's sort of not the point, right? I mean, there's obviously different formalizations or way of doing math in the context of calling it quantum mechanics. But what's the essence of quantum mechanics? And the essence of quantum mechanics is the tricks, like the Broglie trick of saying frequency equals momentum. That's the substance of quantum mechanics, is convert everything that's a linear thing into a wave. Yeah. Once had a colleague who tested his memory, so this is somehow important, memory tests. Apparently he was capable of reciting entire books verbatim that he had read decades ago. Well, I really hate those kind of stories just because that always sounds like bullshit, right? If somebody could do that, then you'd think they'd be recorded doing it. Now, I don't know when he lived, so we can't say for sure we had tape recorders by then, but you'd think, that's a pretty amazing feat. He also could divide 8-digit numbers in his head before most kids learn how to read. Well, that's a nice story, too. So what? I'm just saying, okay, so you think physics is all math. And that's all there is. There's no real mechanisms and real functions that math merely tries to formalize. So when I say that math is just a formalization of what we already know, that is, we see an occurrence and we formalize an equation that pulls out of the occurrence what we understand to be the variables, the things that caused it, like how wide is the slit. We figure, yeah, that changes the outcome. And we figure out the wavelength, well, that changes the outcome. So we figure that stuff out and formalize it in an equation. You're saying that's the detective work. I'm saying that has nothing to do with detecting why it does it. Why does the slit width matter? Why does the wavelength matter? How is the light actually going through the slit and interacting? What's the physics? But you think the mathematical equation merely saying, I figured out a couple of the variables that seem pretty important, that is physics. And yeah, I'm clearly arguing, no, it's not. Okay, before most of the people who develop the physics you bash, no, he didn't develop the physics I bash, so that's just a lie. He's developed the physics I say is irrelevant. Okay, it doesn't mean anything, doesn't do anything really, really constructive in terms of building the model. He didn't build the model of quantum mechanics or the model of the standard model. You tell me what his contribution to the standard model was. On this channel, we're much, much smarter than you. So again, this is a contest of some kind. I would say you're pretty dumb. Okay, if von Neumann believed in bent space, then sorry, you could say he's really smart. But I've seen really smart people do really stupid things. Right? There's really smart people that can't figure out how to even wipe their ass properly. So this doesn't really matter if somebody's really smart by those standards. And smarter than you to the point where you can't even grasp how much smarter than you they were. And you can't grasp how big a failure you are. So I can just make that accusation. You're so deeply fail that you can't even see up to see how far from the prize you are. You're so far down the shit for brain well. Ugh. Pathetic asshole. Alright, last one. Universe doesn't have an obligation to make sense. This is one of the stupidest things any human could ever say, right? Because no one's arguing that the universe has to be reasonable, or that it has to be productive, or it has to go out and get a job, you pay the bills. No one's arguing that. The argument is that statements about things, like things have to have continuity. 2 plus 2 can't equal 3 and equal 4 at the same time. It's just a silly contradiction. It can't be an elephant and a baby duck at the same time. Same thing can't be both of those things. It's a contradiction, a ludicrous contradiction, an unreasonable contradiction. And that's all the argument is about. What are reasonable things and what's unreasonable? This isn't an argument about the universe making sense, idiot. It's just about you can't sit there and have things both ways. It really can't work that way. It can't possibly function being both the light bulb is on and it's off at the same exact time. You can't have two voltages in the same place in a wire. It's obviously a ludicrous explanation. It can't be both ways. Contradiction is ludicrous. And there's absolutely no evidence that the universe does function that way. There's no evidence of the universe committing these insane contradictions. There's only evidence that humans create theories that are full of contradictions. Such an assholes. I mean, they're just everywhere. Gary has just PQ'd that all the nerds in high school, for the most part, ended up with successful lives. Go ahead and show me one of those. You're probably somebody who cares to research all this stuff. Go find the class of '77. All right, from the high school I went to, and you go show me all the brilliant lives that came out of there. Go ahead and show it to me, fella. I'm the lucky one, asshole. Frankly, I mean, really, you actually think I'm sitting here saying, I wish I was one of you? You really think that? I mean, you're that fucking stupid? Holy shit. Here, Gary ended up living in a trailer park. And yeah, I'm the type, man. You know, if I lived in one and I could buy it, I'd probably buy it. Yeah, that'd be really cool. But you really think I'm lamenting I don't have a mansion and a yacht? You really think that's how I'd spend my time? Man, you're stupid. Alright. So we can get rid of them for good. And we'll delete this because it's useless. And we'll leave that because that was pretty useful. Alright, so a lot of crap there. Yeah, so till the next time. And such. Till the next Van Briesen video, hopefully. I'll get to that. And, yeah. Till then. I mean, again, if anybody knows where they've done the experiment with the poles of the magnet being the same poles, and then put a current through the wire, what does it do? I'd be curious. Very curious. So, until the next time. And such.